This grid maze represents our environment. We start at the top left corner with a specific amount of health, and our objective is to navigate step by step until we reach the destination at the bottom right. Every step we take carries a consequence based on the cell's value. Entering a safe cell, marked by a 0, costs nothing. At the final square, with at least 1 point of positive health remaining, the path is considered a success. Look at these two contrasting paths. A direct, short route by distance forces us through 3 dangerous cells. A winding, longer route avoids the danger and only costs 1 health. To survive, we do not want the shortest path by distance. We need the path with the minimum danger cost. To find that minimum danger cost, we introduce a new matrix on the right. It perfectly mirrors our grid, but instead of tracking cell types, it records the absolute minimum number of unsafe cells required to reach every specific position. Since we haven't explored any paths yet, every cell starts at infinity. This matrix serves a dual purpose. By storing the best possible cost, it naturally acts as our visited tracker. It simply rejects any new path that arrives with a higher or equal cost to what we have already recorded. To navigate the grid, we use a deck, a double-ended queue. Unlike standard queues, this structure allows us to insert coordinate data at either the front or the back. By combining a cost-tracking matrix with a 2-sided queue, we create a specialized mechanism that forces our algorithm to naturally process zero-cost safe moves before it ever considers dangerous ones. This split screen shows our exact Java execution on the left and our memory state on the right. When we begin, the code checks the very first cell. If the starting position is unsafe, it immediately updates our sorting cell cost to 1. Inside the main loop, we pull the lowest cost position from the queue and generate all 4 possible neighboring directions. We calculate the cost to reach a neighbor by adding its grid value to our current running total. If this newly calculated cost is strictly less than what our distance matrix currently stores, the code overwrites the old data. Let's pause the execution for a moment. Based on priority, if the successful update comes from a safe cell with a weight of 0, does it go to the front or the back of the DEEG? Safe moves do not increase our danger cost, so they deserve immediate priority. They are pushed directly to the front. Unsafe moves increase the cost, so we push them to the back. This guarantees the cheapest possible paths are always explored first. As we let the loop run, watch how the search aggressively snakes along the 0-weight paths. It exhausts every possible safe move at the front of the queue before it is forced to process the 1-weight paths at the back. The algorithm completes when there are no more useful paths to explore. We can now look at our destination cell and extract the absolute minimum danger cost required to reach it. To verify if the walk is safe, we subtract that minimum cost from our starting health. The final return statement evaluates whether the minimum cost is strictly less than our starting health. We cannot check if it is less than or equal to, because dropping to exactly 0 health means the character fails the final step. Bringing the entire solution together, we can see exactly why this 0-1 BFS algorithm is perfectly suited for this grid. First, the binary values of the grid translate directly into our edge weights, which determines their placement at either the front or the back of our deck. Second, our distance matrix serves as a gatekeeper. By only allowing strictly cheaper paths to process, it removes the need for a separate visited array entirely. Because every edge has a weight of exactly 0 or 1, we avoid using a slow priority queue. Every grid cell is processed efficiently, allowing us to find the safest walk in strictly linear time and space complexity.
First, I calculate the number of rows and columns in the grid. Then I create a 2-dimensional distance array. This array stores the minimum health loss to reach every cell. Initially, every value is set to integer.maxValue because no cell has been visited yet. Next, I create a DEEG, which will be used for 0-1 BFS. The starting cell is initialized with the value present in the first grid cell. I also push the starting position into the DEQ. Now I define the direction array so that we can move in the 4 possible directions: up, down, left, and right. The main processing starts with the while loop. As long as the DEQ is not empty, I remove the first element. This gives me the current row and current column. Before exploring the neighbors, I check whether the health already lost at the current cell is greater than or equal to the available health. If that's true, then this path can never succeed because our health would become 0 or negative, so I simply skip it. Now I iterate through all 4 directions. For every direction, I calculate the next row and next column. The first validation is the boundary check. If the new position lies outside the grid, I simply continue to the next direction. Otherwise, I calculate the new health lost. If the next cell contains a 1, I add 1 to the current health loss. If it's 0, the health loss remains the same. If this new health loss is smaller than the previously recorded value for that cell, then I have found a better path, so I update the distance array with this smaller value. Next, I decide where to insert the new cell in the DEEG. If moving to the next cell does not increase the health loss, meaning the cell contains 0, I insert it at the front of the DEEG. This gives 0-cost moves higher priority. Otherwise, if the next cell contains 1 and increases the health loss by 1, I insert it at the back of the DEEG. This ordering is exactly what makes 0-1 BFS efficient. The algorithm keeps processing cells in increasing order of health loss until either every possible path has been explored or we find a valid path.